Let's continue our discussion of quantum numbers. We're now going to focus a little bit more on the value of L. So the value of L, I've indicated before, tells you information about the orbital's shape. And what we're going to do is use letters to designate what type of a shape we're going to be dealing with for each different subshell that you would have. So if you have an L value of 0, we're going to designate those as S orbitals, or we would say this is an S subshell. When you have an L value of 1, we would designate those orbitals as p orbitals, and we would say this is a p subshell that we're dealing with. For L of 2, the orbital designation is d, and for an L value of 3, the designation is f. You have to make sure that you're aware of what these letters mean, and know that anytime you see an L of 3, that's the same thing as a designation of f, or if you see a designation of f, you have to know that means that the L value is 3. With that in mind, let's apply that information to what we've seen already when we looked at the orbitals that we had in the n equals 1, n equals 2, and n equals 3 shells. So in the n equals 1 shell, there was only one subshell allowed, right? Because we only had one value of L that was possible. This value of L was 0, and so this is an S subshell. What we will say is that this is a 1s subshell. The coefficient of 1 indicates the principal quantum number. So we're in energy level 1, and then it's an S subshell because the value of L is equal to 0. All right, let's go on to the n equals 2 energy level. In the n equals 2 energy level, we had two subshells. The first one had L equals 0, and so that's also going to be an S subshell. We're going to call this a 2s subshell. And in the case of n equals 2 and L equals 1, well, the coefficient is 2 because we're in the n equals 2 shell. And then for the subshell designation, an L value of 1 means it's going to be designated as a P subshell. So we'll call this the 2P subshell. For the n equals 3 energy level, for n equals 3 and L equals 0, we'll call that a 3s subshell. For n equals 3 and L equals 1, we'll call that a 3P, right? Because when L is equal to 1, P is the designation that we use. And then for n equals 3 and L equals 2, when L is equal to 2, the designation is D. So this is a 3D subshell here. Or we would call all of these orbitals in the subshell 3D orbitals. Now, it could be very cumbersome to write out all of this information. So something else that's helpful to do is to represent all of these orbitals on an energy diagram. And instead of writing all the quantum numbers for every single orbital, what we can instead do is use these designations. And we'll also represent each orbital by using a horizontal line, as you'll see on the next slide. This is a diagram that shows all of the orbitals that you just saw on the last slide. And every horizontal line represents one orbital. Now, importantly, in this diagram, and when you have a one electron system, all orbitals that have the same principal quantum number will have the same energy. That's not a big issue for the n equals 1 energy level, but for n equals 2, when you have multiple orbitals, that does become important. So the orbital that's in 2s is equal in energy to all of the orbitals that are in 2p, right? And then for n equals 3, the 3s, 3p, and 3d subshells are all equal in energy. Now, notice from what we saw before, in an S subshell, you only saw one orbital in that subshell, right? In every instance, when you had L equals 0, there was only one ML value allowed, right? So there's always one orbital in an S subshell. P orbitals always come in sets of 3, because when you're dealing with P orbitals, you have L equals 1, and whenever L is equal to 1, ML can be 0 plus 1 or minus 1, right? That's 3 orbitals in every P subshell. You see it in this one, and you see it in this one. So that's why when we look at the 2p and the 3p subshells, we have 3 horizontal lines to represent those 3 orbitals. D orbitals always come in sets of 5, because when you're dealing with a D subshell, you have L equals 2, meaning that ML can take on 5 different values, 0, plus 1, minus 1, plus 2, and minus 2. So that's why there's 5 lines here. And so this is a quicker way of representing all of the information that you just saw in the last slide. And we'll even see some faster ways of representing it as we go on to discussing electron configuration. But up next, what we're going to do is take a closer look at these orbitals, and we're going to talk about the wave functions that describe these orbitals, and we're going to talk about what the actual shapes of the orbitals look like. So you're going to see some actual images to help you visualize these different orbitals.